A very good evening to everyone. We, the team of Petroleum Engineers Association, is delighted to organize webinar session on the theme Hydraulic Fracturing Basics and Operational Overview. We are very pleased to introduce Mr. Yes Bhatt sir, who will be our speaker for today's session with 9 plus years of experience in oil and gas industry. He is integrated service website leader, regular operation at Schlumberger. At this time, I would like to inform you all that there will be a Q&A session at the end of the presentation. However, you can submit your queries related to topic using the chat window on the screen. We will also be posting the presentation of the webinar on our LinkedIn official page so that you can access it anytime and video on our YouTube channel. Now, I would like Yusvat sir to start the webinar by sharing their knowledge on hydraulic fracturing, basic and operation overview. Thank you.
Okay, so hi guys, am I audible to all of you? Hello?
Yes, sir.
Okay, so let's start with the hydraulic fracturing basics and operational overview. Hydraulic fracturing is a widely used technique in oil and gas field production optimization, and it is quite an old technique. And basically, it's a mix of all the three aspects of science that you have studied. It's physics, chemistry, and maths. So everything goes into planning, designing, and executing this kind of operation. Okay, so this is a common practice, and the use of hydraulic fracturing is increasing day by day because most of the fields in India and abroad are maturing. And we Indians and India as a energy-starved country, we definitely need these kinds of techniques to enhance our oil and gas domestic production, right? So we'll be briefly discussing about the process and a little bit of its basics so that all of you can get an idea about what hydraulic fracturing is and why it is done. Okay. So let's start with it. So I think the term must be common to all of you. If not, a generic person will think that while hearing hydraulic fracturing, or it is also called fracking. So what is hydraulic fracturing? So the question might arise. People might ask why we should do hydraulic fracturing. And if you know why to do and then how to do it is another question, right? And then what type of fluid and proppant is used in hydraulic fracturing? So fluid and proppant, these two terms I'll explain while I'll be continuing with my presentation. Okay. So this is an introduction of what is hydraulic fracturing, or it is also called hydrofracturing. So it is basically a process of creating artificial fractures in the reservoir by pumping high pressure sand laden fluid. Okay. So some reservoirs, they are, if you are aware of the term permeability, okay, each and every reservoir has some permeability. So some permeability, some have great high permeability, and some reservoirs have low permeability. So basically, in reservoirs which have low permeability, and in the formations where the damage has occurred due to drilling and other practices, there this technique is very common. Why it is done? In some reservoirs, to get economical oil and gas production rate. Sometimes your well is producing, but it is not producing too fast. So your management might think that, okay, now the oil price is high, so I must produce as fast as I can and just make the most out of this opportunity. So they will consider to hydraulically fracture the reservoir and increase the flow rates so that they can make use of the opportunity. So what is to be done? A conducive fracture or crack in subsurface formation, it provides an easier path. So if you fracture a formation, it will provide you an easier path for the fluids so that they can flow into the wellbore and at a very less pressure drop, right? It is similar to driving through a crowded street and driving on a highway. So if you are driving through a crowded street, your speed will be very low. Your vehicle will not give enough mileage, and you will be facing hindrance from the front, right? So you'll not be getting from point A to point B in a shorter span of time. In contrasting to that, if you are on a highway, so you can drive as fast as you can, You may be gaining on mileage, and the time required for reaching from point A to point B would be less. So similarly is with hydraulic fracturing. So if you crack open a conductive path in the formation, so oil and gas, they will be traveling at a much faster rate through that highly permeable and conducive channel to the wellbore. Okay, so your production will be increased. Continuing on that, why it is required to enhance productivity. See, before any while drilling, a lot of fluids are used, like mud and different kinds of mud and different which has different kinds of chemical in it. So while drilling, the mud is to be circulated in the hole. So if you have studied drilling and engineering, you must be knowing that. So that mud and other chemicals, sometimes cement also, it causes a sort of formation damage into the formation, and it disrupts the natural occurring permeability of the reservoir. Okay, so this creates a skin around the wellbore. Skin is basically a damaged zone through which the oil and gas cannot pass. Hydrocarbons cannot pass, or they have difficulty to pass through it. So to bypass that damage, fracturing is to be done. So path is cracked open through that damaged zone from the wellbore into the reservoir, so that hydrocarbons can flow easily. To increase the conductivity in lower permeable formations. Some formations have naturally lower uh, permeability. So to increase conductivity in such formations, we require them. Required to be, this fracturing operation is required. To generate high conducive path, as I already told you, to improve and accelerate the recovery rate of the well. So the picture right at the right end of it, the bottom picture, so it is showing the flow of hydrocarbons in a fractured reservoir. So the two white lines in the center there is well, and these two white lines are the fractures. These two lines, okay. So we also call them fracture wings. So if a reservoir is fractured and these fracture wings are created, and this black portion is the formation or matrix itself. Okay, so the oil and gas, the hydrocarbons, will travel to this fracture, and then from there they can easily traverse to the wellbore from where you can lift them. Okay, so this is like a highly permeable channel you have created through hydraulic fracturing operation. So how it is done? So a set of equipments is required for this operation to be conducted. So collectively they are known as hydraulic fracturing unit or HF unit or frac fleet, you can call it. Okay. So this frac fleet generally comprises of a fluid storage, some sand or proppant. I'll be discussing that later in the presentation. Then they are mixed through a equipment called blender. So it blends your frac fluid as well as your proppant. And then this proppant and fluid, the mixture of it is called the slurry. And the slurry is then sent to the pumper, which increases the pressure of this slurry and pumps into the wellbore through the wellhead. From the wellbore, it goes to your formation. Okay, so this is just a basic overview of fracturing operation. So what are the frac equipments? Let's discuss them in a little bit more detail. So first is frac tanks. So these are water storage tanks. So these are water storage tanks which are used to store the water which is required to mix the frac fluid. Okay, so they are high capacity tanks. The second is hydration unit. So hydration unit is a unit which is used to prepare the frac fluid. So certain chemicals are to be mixed in water before we can prepare the frac fluid and we can pump it downhole for the fractures to be created, right? Then there is blender. So the function of blender, as I also told you before, it is to mix the frac fluid and the proppant sand together so that they can further be pumped in the well. There are frac pumps. So this is just an example, 6000 hp. So the pumps need to require a certain hydraulic horsepower. So the requirement of hydraulic horsepower will again depend on what kind of formation you're dealing with, what kind of fractures you want to create, and what kind of pressures are you expecting in your well while fracturing. So you'll select your pumps accordingly. I'll briefly touch that point also. Treating irons. Treating irons are basically high pressure pipelines through which you will pump your slurry into the wellhead and into the formation subsequently. Right, they are high pressure lines. They are capable of holding pressure up to 20,000, 25,000 psi, like that. Frac 1, it's basically a data acquisition center. So while you are fracturing, you will monitor all the parameters and record your pressure trends and everything. Frac stack, it's basically the wellhead, which is used to pump the slurry into the well and then into the formation, right? So the wellhead it comprises of various valves and various wellhead accessories which allow you to pump that slurry into the well. Flow meters and pressure transducers. So flow meters are required to measure the flow rate, at what rate are you pumping. And pressure transducers, they allow you to read the pressures on various lines, such as your treating iron and all, and wellhead pressure and everything. Pop-off safety valve. Okay, so most of the hydraulic fractures are pumped through the casing, the production casing. And the production casing, it is also a metallic pipe and it has a burst rating, right? So it cannot be pressurized beyond a specific value. So to prevent that from happening, a pop-off safety valve is used. Okay, so you can set the pop-off safety valve at a certain pressure beyond which you would not like to increase your pressure. So if that pressure is reached at any point during a frac job, your pop-off valve will open and it will not allow the pressure to go beyond the set limit. Acid tank, if you want to pump some acid, now acidization is generally done prior to the frac jobs because you might want to remove some debris or some metallic content that might be there present in the perforations. Okay, so for that acid tanks is used. It's not necessary to pump acid in before any frac job, but it is kept as a contingency. Iron basket, it will hold all of your irons and everything in one place. Sand king. Sand king is particular sand silo in which you store your proppant and you deliver it to the blender for mixing as your frac job continues. So sharing some pictures of the equipment. So the picture on the left is a twin pod water filtration unit, and on the right there are frac tanks. So the frac tanks, they store water, and but for to make frac fluid, the water should be of a certain quality. There are certain parameters like hardness, the TDS, the TSS, which have to be maintained for the frac fluid because you want the frac fluid to be a good quality. So sometimes the filtration of water is required for the removal of any debris or any suspending particles. So this twin pod filtration unit is used. There are membranes which filter out the water from to remove all the debris, and the size of that membrane is in microns, around 8 or 10 microns. And you can also design it on the basis of your requirement. So this is a LFC batch mixer. Some companies, they use a term called LFC, liquid frac concentrate. It's basically a thick fluid which is then diluted to make a frac fluid. So that thick fluid is mixed here. It is a vertical tank which has an agitator inside. So you mix all the chemicals which are required to prepare that frac concentrate and just churn it into the tank, and your frac concentrate, it is mixed. And then that frac concentrate is diluted in the hydration unit. So in the hydration unit, you mix the liquid frac concentrate and water in a certain proportion, which will give you a frac fluid of desired viscosity. So this particular unit, hydration unit, it has some inline viscometers so that you can monitor your viscosity of frac fluid at all times, and you can also vary it according to your requirement. So the next is Sand King. Sand King is basically a sand silo. So if you can see the diagram, there is 1, 2, 3, 4 written on it. This is particularly a Baker unit, BJ unit. So it has different compartments. So different kinds of proppants can be stored inside it during job. So this is the heart of the fracturing equipment. This is called a blender. So the blender mixes the frac fluid and the proppant. Now the success of jobs, of a frac job, it depends largely on the quality of the mixture that a blender can produce. Okay, so if the mixture is not homogeneous, there are chances that your frac job cannot go properly. So it has to be a homogeneous mixture, and there is something called shear rate at which the blender mixes the proppant and your frac fluid, that has to be adjusted in such a way so that your frac fluid does not disintegrate and your entire slurry remains homogeneous. From the blender, your slurry goes to the pumps. So these are the couple of pictures of frac pumps. They increase the pressure of the slurry, which is to be pumped in the well. And then the selection of the pumps is dependent on a lot of parameters. As I also said before, on your size of completion, your type of completion, what formation are you dealing with, what pressures are required for fracturing that formation. So selection of pumps is done on the basis of a pump performance curve. Similar like your car, if you know how to drive a car, there is a certain speed at which you can go at a particular gear, right? So at first gear, you can go up to 10, 15 kilometer per hour. So then after 30, up to 30 kilometer per hour, you can go into second gear, and then so on. So same way, the pump pressure is governed by the RPM at which the pump's engine is rotating, right? So at what rate do you want to pump the fluid into the well, and at what pressure? So these curves, they will help you to select the correct pump, that, oh, okay, this is the pump I require for pumping this job. So not all the jobs may require the same kind of pumping system. They might require a different kind of pump with a different hydraulic horsepower rating and a different type curves. So you have to understand this. Okay, so this graph shows at what rate, what is the maximum pressure that you can get, and at what gear. So the pump operator basically should be aware of the pump curve, because he's the one who's going to operate it. And as an engineer, you should be aware of the equipment's limitation and its the kind of performance it is about to give during your frac job. So let's talk about the wellhead a little bit. So when you're pumping a frac job, you have to have certain equipments at the top of the well to contain that pressure, right? So these irons that you can see, which are going down to the ground, these are your treating irons. These are basically your pipelines through which you pump your job. And this something is called the frac head. There are walls on top of frac head. These are gate walls or master walls, you can call them. So these are, in this picture, they are 10,000. They can hold a pressure of 10,000 psi, up to 10,000 psi. So these walls are to be pressure tested before you can pump any frac job in the well. Otherwise, you might observe a leak and your job will have to be stopped, or it might fail also. So this is just the generic site view, how a frac site looks. So basically, these are your pumps. This is one pump, this is one pump, this is one more pump. Can you see the pointer moving? Hello? Okay, thank you guys. So just a minute, I'll go back to that slide. So this is a side view. So these are three pumps, and these are the irons through which you are pumping your sand-laden slurry into the well. Okay, so there is a simultaneous operation, which is coil tubing is also there. So I'll briefly touch about coil tubing also. So this is your wellhead, and there you're pumping it down. Right? So this is just a typical, just to get you a feel of the operation, how it is, how it happens. So let's discuss briefly about coil tubing unit, because I'm going to cover up multi-stage fracturing operation, which is an operation which is carried out with coil tubing and a fracturing unit. It's an integrated operation. So let's discuss about coil tubing unit so that you can understand better. Okay, so what is a coil tubing unit? It is basically a continuous pipe unit which you can run into the well to do multiple kind of job. The versatility that the coil tubing unit it brings to the table, it's impeccable. You can complete multiple kinds of job. There is no end to it. But for this particular operation, we use the coil tubing unit to create the perforations in the well. Now, why perforations are required? Because your completion is basically your production casing, and there is cement behind it because it is cemented, and then there is formation. So if you want to pump into the formation, you have to first create holes in your casing and through your cement and to your formation so that you can communicate with your reservoir, right? So for making those cuts, for making those holes, a special BHA is used, a bottom hole assembly is used. So the bottom hole assembly is which is used for sand jetting perforations. It has small tools with small nozzles which have really small diameter like 0.18 inches or something. So if you pump the sand slurry through it, it will come out in form of a jet, and it will cut the casing, and it will also cut the cement behind it, and it will also cut into the formation up to certain length so that your communication with the formation can be established, right? So let's go over this slide. So coiled tubing unit is portable hydraulically powered system designed to run and retrieve a continuous string of. So the main advantage of coiled tubing units is you don't have to add more pipe, because if you are working with a rig, so you have to run a pipe, then again make a connection, then you have to run it again, then you again have to make another connection on top of it, then you will run. But coil tubing, it is a pipe wound on a reel, so you can run it continuously. During your internships, if you might get a chance to see it also. Right. So what are the components of a coil tubing unit? So this is the reel on which the pipe is wound. Now this is the pipe. It goes to an arch, which is also called a tubing guide or a gooseneck. Then you have your injector head. This assembly is called your injector head. Okay, so these have this injector unit. It has drive chains which push the coil tubing into the well. Right. Then you have a blowout preventer stack. So this is a blowout preventer. I think if you belong to petroleum engineering, you all be knowing what a blowout preventer is. So it is a mandatory requirement to have a blowout preventer whenever you are doing any intervention job on any well. This is a government guideline as well as it is the best safety practice among the industry, right? So we'll discuss about it also. So there is hydraulic power drive unit which powers the entire system. It has a hydraulic circuit. So all the controls of coil tubing unit are for the power for those controls is given by the power pack. And there is control console which is in the coil tubing unit compartment. So this is what it actually looks like. So this is your reel, and this is your coil tubing unit, and this is your control cabin. Okay, and this part is called power pack. So it gives a supply pressure to the control cabin, and from there you can operate all the controls in this coil tubing. Okay, so coil tubing comes in various sizes from 1.75 inches, 0.5 inches, 1 inch, 1.5, 1.75, 2 inch, 238, 278. So that is according to your operation design that which coil tubing you want to use. Okay, so injector head I already explained. So this part is called the gooseneck or the guide arc. Okay, and these are the injector chains which are hydraulically powered, and they push your coil tubing into the well against some pressure. So now BOP, it is very important piece of equipment, and as an engineer, when you will be hired by some company and you will be required to perform a job. So it is a mandatory requirement for all the well-related jobs. Without BOP, no jobs can happen, and you should not do that without any BOPs, right? So this is a quad ramp. Quad means 4. So it has 4 different types of ramps. First of all, let's start from the bottom. So these are tubing ramps at the bottom, right? So tubing ramps, or it is also called pipe ramp. So when you engage these kind of ramps in sorts of event, so if suppose you are running your coil tubing in the well and a blowout is happening, so to prevent that influx to come onto surface, you have to engage your tubing ramps or pipe ramps. So what they will do, they will seal off the area between your coil tubing and the production casing, so that from between the coil tubing and production casing, no influx can come onto surface, right? Second is slip ramps. So slip ramps, they have slips. Slips are basically protruded profiles which will bite on your coil tubing unit, and they will prevent it from being thrown off or being sucked into the well. Right? So they will keep your coil tubing in place. Shear ramps. Now shear ramps, what they do, they have a sharp profile, and if for some reasons the coil tubing is required to be left in hole, they will, if you engage shear ramps, they will cut your coil tubing unit, cut your coil tubing, and uh, seal off above your BOP, so that the pressure which is coming from the well, it will remain inside the well only, and it will not be hazardous on surface, right? And blind ramps will also seal off above the cut part of the coil tubing unit, so that any pressure, it cannot come on surface, and the surface equipment and the people, they are safe, right? So this is, so how this happens. Now most of the companies are going for multi-stage fracturing. What is multi-stage fracturing? Multi-stage fracturing is when you want to frac more than one zone in a single well. Okay, so earlier there were one zones were fractured in one well, so but now that was not being considered economic. So people are going for multi-stage fracturing everywhere. It's happening. Okay, so this is the brief animation, so which will show you how this happens. So the gray part here, these are basically your formation. This is the first formation at the bottom. This is the second formation at the middle, and this is the third formation. And now through a single well, you have to fracture all three of them. Okay, so how to do it? So these kinds of operation are run with the hydraulic fracturing unit in conjunction with the coil tubing unit or a wireline unit. So here I'm emphasizing about the coil tubing unit. Okay, it's very easy to understand. So this is the well, and these gray parts are the reservoirs that you need to frac. So what will you do first? So you will run the coil tubing unit and run the coil into the particular depth at which you need to create the perforations, right, for to establish communication with the reservoir. Then you will pump a sand laden fluid into your coil. So now this sand laden fluid will be slightly different. This sand can be a natural sand, also naturally occurring. It may not be a sorted sand, because you just need to make the cuts in the casing and in the cement to establish communication with the reservoir, right? So we'll pump it into the coil tubing unit through the coil, and this is your BHA bottom hole. And as I told you before, BHA has a nozzle. So through the nozzles, the sand slurry will be jetted across your zone. So due to this jetting effect, the sand slurry will cause an abrasive effect, and it will cut the casing as well as the cement, and it will cut up to certain depth in the formation. Okay, so now you have, when you have made these cuts, you have an access to the reservoir, right? So after that, whatever sand that you have pumped here, slurry, you have to clean it out. So you will perform a clean out in a forward circulation. So what is forward circulation? It is when you pump through the coil tubing unit and take the returns through the annulus. Okay, this is called a forward circulation. So you'll clean out everything so that you do not leave any sand in the wellbore. What's the next step? So this is the clean out that you have done. Now there is no sand and your perforation is there. So now you have accessed the reservoir. Now you'll pull your coil tubing unit to a certain depth. You will not completely pull it out of hole. We do not do it because we have to save some time, and because time is money in oil field. So we will only pick up your coil tubing up to a certain depth. Then we'll start pumping our hydraulic fracturing operation. Okay, so we'll pump your hydraulic fracturing job into your first zone with the sand slurry. and you might want to keep some sand in the hole because it will act as a plug, okay, so that you can access your second reservoir. If you do not plug this reservoir, then because you have hydraulically fractured it, it will obviously have more permeability than your other zones. So if you do not plug it and you pump fracturing job for the next zone, all the fluid will be taken by this particular zone, which is already fractured, and the other zone will not be fractured. So the plugging or zonal isolation is required for this. Okay, so then after pumping the first frac job, you clean out, and then you go for the cuts in the second zone. So you have made the cuts, you have done the clean out again, and then you pick up the CT up to a certain depth, and then you pump your second job. Okay, so similarly, you can do these operations like this. Okay, so in this example, we have pumped 3 frac jobs in one well, okay, without causing too much time delay because we did not pull out coil tubing unit, and we saved a lot of time. Okay, so this is called multi-stage fracturing because multiple stages. So this is stage 1, this is stage 2, and this is stage 3. So there are different stages, right? So after that, when the well is all the fracturing jobs have been completed, you can run the coil tubing on it again and clean out the remaining sand, and then your well is ready to produce. So this is another animation. So the yellow part which is going down when what you're pumping down is called pad fluid. So we'll discuss it now. What is pad? And behind it, it is sand slurry. So when you're pumping it into the formation, your pad is going first. It is making the fracture, and then you're filling it with sand slurry, right? So what is pad fluid? Pad fluid is basically the same frac fluid without any sand. It is pumped first. It is pumped first so that you can first create the fractures in the reservoir. Okay, so if you do not create fractures first and you straight away start pumping sand, it will be all the perforations will be choked and you will not be able to pump anymore, right? So some space, some volume is to be created in the formation first for it to be able to accept the sand that you're going to pump. Okay. So first you will pump pad fluid. Okay, so you are pumping pad, and from the blender, you are also pumping the sand slurry. So your pad is hitting the formation first, then you are pushing the pad into the formation and displacing it with the sand slurry. Okay, so the pad will continue to create fractures and the sand will follow it. So wherever the pad fluid goes, the sand goes. And at the end, the brown part, this is the displacing fluid. When you have pumped all the sand that you wanted to pump, then you pump flush. It is just a clean fluid which is to flush all the sand so that your wellbore does not have any sand and all the sand is pushed into the formation. Okay. So the fracture which is created like this, it's called a propped frac because the sand is called the proppant. Okay, so we'll discuss about the proppant a little bit. So if you have any confusion about this process, you can ask me later, right? So we have been talking about frac fluid a lot, and let's discuss what is actually frac fluid and how should we select it. So good frac fluid system, it should be capable to create and extend fracture. Okay, because whatever is the reservoir, it will have a natural permeability and it will have a natural matrix which will allow any fluid which is pumped inside it to leak off. Okay, so for the fracture to be created, we need to minimize this leak off. Okay, so the selection of frac fluid should be such that this leak off is minimized so that your fluid can stay in your fracture and create a path for the subsequent sand slurry, which is to be pumped, right? So it should be able to create and extend fractures. It should be formation compatible. It should not react because when you're in the formation, there is a bottom hole temperature, and at that which is higher than the surface temperature always because of geothermal energy, right? So at that temperature, the rates of reaction they tend to increase. So your fluid should not be such that it might react with your formation rocks or formation fluid in such a manner which can damage or hinder your frac operation. For some reasons, it might create a it might react with the rocks and formation fluid, and it might create a solid substance which can choke the perforations, and it may not allow you to pump a frac job because perforations are the only entry point for the frac fluid to enter. So if they are choked, you won't be able to pump. So the compatibility is to be checked every time you use a new fluid or before you even prepare it. So there are core samples which you take during drilling. So you should check the compatibility of the fluid that you're going to use with those core samples. Okay. Now it should be capable of suspending proppant and transporting proppant up to the tip of the fracture. So proppant is the sand. Okay. So it should be able to. So where are you mixing your sand and your frac fluid? In the blender. So straight from the blender up to the tip of your fracture in the reservoir, it should be able to suspend your proppant. Okay, just imagine there is a bucket full of water and you put a sand, uh, fistful of sand in it. What will happen? It will just settle in the water. Okay, now just fill the same bucket with the honey, and then you put sand in it. What will happen? It will be suspended on the honey and it will settle more slowly, right? So that is the part viscosity plays. So the fluid should be having such viscosity so that it should not let the sand settle in the pipelines or in the formation. You should always be able to keep your proppant in the suspension or in the slurry mode. It should not solidify so that it can flow. Right. So capable of developing the necessary fracture width. Okay. So now the width, we are talking about the frac geometry that this point I'll take later. So from the perforations, they should be big enough to allow this sand slurry to enter. Okay, so this fracture width is to be created so that your sand slurry can enter into the formation. It should be efficient, low fluid loss, because fluid loss it is bound to happen because all metrics will has some leak of properties, and it will continue to leak off until you seal those leakages off. Okay, so it should have leak off properties or fluid loss control properties. Okay, it should be easy to remove from the formation. So now when this frac fluid is prepared, there is one additive which is added is called breaker. So now why do we need breaker? Because whatever fluid we have pumped in the formation, we do not want it to stay there. We want it to flow back so that it cannot cause damage to the permeability that you have created or the proppant pack permeability that you have created over there. Okay, so you have to remove that back. So for the removal, you have to break the fluid. Okay, because the same high viscosity fluid that you have pumped, if you want to flow the same high viscosity fluid, it will also bring the sand with you back, which you do not want. So the viscosity is to be broken first. So these breakers, chemicals are added into the frac fluid so that that viscosity can break and you can recover just the broken fluid. Now, when the fluid is broken, it might produce some solid residue, which can damage your proppant pack permeability, which you have created after fracture. So you don't want that, right? So the fluid should be as clean as possible, and it should not be producing any fines or any residue in the formation, so that when you recover the fluid, the the channels that you have created while fracturing, they remain open. Possess low friction pressure. Okay, so now the friction pressure, if any fluid is giving high friction, okay, it should not, it will affect your pumps because more pressure would be required to pump the fluid if the friction is very high. So it should be having low friction properties. It should be simple to prepare, and definitely cost is going to be high. So what kind of fracturing fluids are there? There are oil-based that were used. They're part of history now. So water-based fluids, they are generally nowadays water-based fluids are used. So now we have something called cross-linker gels also in the formations which are deep and they have a high temperature, because temperature has a effect on frac fluids. So it can break the frac fluid. So we do not want that. Okay, so some cross-linking agents are used for the in the frac fluid recipe so that it can attain a higher viscosity. Somewhere energized or foamed fracturing fluids are used. We can also use propane, the gas, for fracturing in some places. Now there are some surfactant-based fluid. So these are variety of fluids which are used for different purposes. So what are the additives? What do you add in a frac fluid? How do you prepare it? Okay, so there is a buffer solution. So when the frac fluid should have a proper viscosity, and to impart that viscosity, you have to add a gelling agent, which is guar. Okay, so now if guar is to provide a viscosity to a certain frac fluid, the pH of it should be neutral. So that's why buffering agents are used, so that you can, if it is acidic, your water is acidic, then you can bring it to neutral pH. Bactericide. Now bactericide, they prevent the growth of bacteria in the water, because if bacteria is there, guar is a natural organic polymer, so the bacteria will degrade it and it will hamper your frac fluid. So you need to add bactericide. Flowback additives, they help the frac fluid to flow back on the surface. Next is iron control. So if there is any acidic environment in the formation, or if you are pumping acid, then it should not cause any precipitation of iron particles, okay, or metal oxides. So because they can definitely plug off your perforations or any conducive channels. So you do not want that. So you need to add iron control. There are breakers, as I discussed. There are two types of breakers. One are oxidative and other ones are enzyme breakers. So these are two types of breakers. So the concentration in which you'll be mixing these chemicals, that is called a fluid recipe. So this recipe is to be identified and it is to be finalized before pumping all the frac jobs, so that you can mix the chemicals on fly while pumping your frac job. Corrosion inhibitors, they are used if you're pumping acid, or if your fluid is capable of causing corrosion in your downhole tubulars, then a corrosion inhibitor is must have. Now let's talk about proppant. Okay, what's proppant? Proppant is something you need to pump with your frac fluid, because frac fluid will leak off, and you will, or maybe some part of it you will recover, but the fracture has to, that you have created, it has to remain open, because if the frac fluid leaks off, your fracture will be closed again, right? So it should be closing on to something. So this is the proppant sand which we use as a propping agent to keep the fractures open. Okay, so a good proppant, should be the characteristics of a good proppant? It should be able to keep the fracture open. So when the fracture is closing, it will have a lot of stress on the sand which you have placed, or sand or proppant that you have placed on it, right? So the proppant should be able to withstand that pressure or that stress, and it should not crush, because if the proppant crushes, it will generate some fines which may also cause plugging of the perforations or the fracture that you have created. So the selection of proppant is done such a way that its strength is tested, and your bottom hole closing pressure is tested, so that you can use correct kind of proppant which does not crush and it keeps your fracture open. There are certain parameters, sphericity and roundness. So it should be round in nature, and it should be as close to a sphere as it can be. Okay, so that the permeability is more, because if you arrange spheres in a particular pack, they will have more permeability than a pack of particles which are not spherical, right? Acid solubility should be less than 2%. Okay, so they should not be soluble in acid more than 2%. So all these tests are conducted while you are purchasing proppant or while you are accepting a lot of proppant. All these tests are to be done, and then only you should approve that kind of proppant to be pumped with your frac jobs. Okay, the important thing next is the mesh size. Okay, what kind of mesh, what size of proppant should you pump? Okay, so generally what I have pumped and what most of the companies are pumping is 2040 and 1630 size, mesh size. Okay, you should be studying about mesh size more. I'll not elaborate that here because it's a again big topic. So there is a analysis which is called sieve analysis. So in sieve analysis, 90% of your, if you're going to use 1630 sand, 90% of your sand should be lying between 16 mesh and 30 mesh. Similarly, if you're going to use 2040 mesh, 90% of your sand sample weight should be lying between 20 mesh and 40 mesh. So it works like that. Also, it should be cost effective. So what is the selection criteria? So as I emphasized before, selection of proppant depends on closure stress. At what stress is your fracture closing? Because your proppant particles will be subjected to that pressure. So they should be able to withstand it. So the bigger is proppant size, higher is the conductivity. The bigger is the size, the more would be the width of the propped channel and the more will be the permeability. But there is a disadvantage. Bigger proppant also tends to crush more. So you have to strike a balance between your proppant size and the crush resistance. So what we generally use in India, what I've done, companies are generally pumping 1630 and 2040 mesh size. And for hydrojetting, the sand jet perforations which coil with coil that I explained earlier, 2040 mesh is generally used. And for main frac operations, 2040 and 1630, or companies might use a mixture of these sands as well. So overall operational cycle of the hydraulic fracturing, how does it look? Okay, so first you select the site and you do some civil work, you level the ground, and you prepare the paths so that your all the equipment and every equipment is heavy and it is over dimensional, so it should be able to move on the site, right? So you have to prepare the ground for that. Then you move your equipment and you rig up the entire setup. Then you pressure test all the tools and surface lines, because during the pumping, if you observe a leak, then you might have to stop the frac job, or you might hamper the quality of the frac job. So you do not want that. Then you correlate the depth and perforate with coil tubing. Perforating at right depth is very important, because if you end up perforating at wrong depth, which is not your zone of interest, your frac job will be in such a zone which you do not want to be fracked. Okay, so that situation should be avoidable and should be avoided. Now, injectivity test and acid job if required. So if it is the formation is having a lot of pressure and it is requiring to have acid jobs, you should pump acid, otherwise you should not. And then you go to the frac job. Okay, and then go to the next location. So this is the generic operational cycle. So what are the common terms of hydraulic fracturing? What do we use? So some of them would be self-explanatory. If you do not understand them, ask me after the presentation, I'll tell you. So surface treating pressure is the pressure. Treating pressure is basically the wellhead pressure, what you are seeing on the wellhead during the frac pumping. Okay. Then bottom hole treating pressure. So if you add your hydrostatic pressure at the depth of the perforation and the surface pressure and the friction caused by the perforations, this will give you a bottom hole treating pressure. Okay. ISIP, instantaneous shut-in pressure. This is very important term, because as soon as you are done with your frac job and you have flushed all the sand inside the formation, then you shut down your pumps. And at that point, what is the pressure you are seeing at the wellhead? That is called instantaneous shut-in pressure. At the instant of shut-in, because at that time, because the pumps are shut in, the fluid has stopped moving, and all the friction effects of the fluid have been nullified. So at that time, the pressure, what the pressure is, it will give you a good indication of what is the pressure required to keep the fracture open. Friction pressure. Okay, you understand that there is pipe friction. So because your fluid will be pumped through different tubulars of different diameters and different make, so it will impart friction on your pumps. So that would be an additional pressure. Right? So breakdown, at what pressure your formation or the reservoir rock is breaking down, it is initiating a fracture. So this is called the breakdown pressure. Net pressure is basically, I'll cover that point in the next. There is a graph which is to be shown to you. So in that closure pressure is basically the pressure at the time of closing of the hydraulic fracture. Okay, at the time of closing, so that is the minimum pressure that is required to keep the fracture open. So closure pressure, it basically influences all of your job designs and all of your fluid selection and proppant selection criteria. Net pressure gain. So during your frac job, how much pressure you have gained, because the fracture tends to increase during your frac job because you are filling it with sand. So volume inside the fracture decreases on a continuous basis. So the pressure will be rising on your pumps, right? So that is called the net pressure gain. It is also the difference between your closure pressure and ISIP. Now, what is pad stage? As I told you before, pad stage is the frac fluid stage without any proppant. You pump it first to create the frac geometry. Slug stage is a small stage in which you will pump a smaller concentration of the proppant just to check whether the formation is accepting a sand or not. Only after that you will start the actual sand stage. Ramp stages are when you vary your concentration of sand in a sand slurry. So you are ramping it up. So these are called the ramp stages. Hold stages, if you're continuing with the concentration of a particular PPA or particular pounds of proppant added or proppant concentration, if you're holding it, so then it is called hold stage. That means you're continuously pumping at the same concentration, right? You're not varying the concentration. Clean volume is the volume of the frac fluid. So when it is mixed with sand, it is called a dirty volume. What is the flush volume? So how much flush volume you have to pump to flush the entire wellbore sand into the formation. Okay, so that is called the flush volume. What is the screen out? If you're not able to pump the job and in between a sand stage and your entire wellbore is filled with sand, so that and you're not able to pump anymore into the formation, so that situation is called a screen out. So these are to be avoided because they will require a lot of time to because you will have to clean the sand because the entire wellbore will be filled with sand. So just to reattempt your job or going for the next job, it will require cleaning out of that sand first. So all these things are to be avoided. Tip screen out is the screen outs. These are the good thing basically. Tip screen outs are screen out when your entire job is finished and you are just about to complete the flush stage. So tip screen out would mean that whatever the geometry that you created in the fracture, that has completely been filled with proppant, and that's what you want. Now the flow back. So after the frac fluid breaks because of the influence of the breakers that you added, you have to flow the entire volume back. Okay, sometimes you do not flow the entire volume. You maybe flow 30% because the rest of the fluid gets lost in the formation. Okay, so that's called the flow back. So what factors affect the design? The selection of fracturing fluid, it should be able to carry proppant and it should have a fluid loss coefficient that is minimum, as I told. The selection of proppant, it should be based on in situ stresses, whatever is the closure stress is there, on at what stress or what pressure is the fracture closure is happening. That is the key parameter to have the proppant designed. And the bigger proppant, bigger permeability would be there, but also crush would be more. So you have to balance between the two. What is your treatment pressure requirement? What is the pressure that is required to be given from the surface? So that will again impact your selection of equipment and the selection of wellhead accessories. The select the treatment sites. Okay, how much sand do you want to pump? That would depend on the formation thickness. That okay, this is the thickness of the zone that I'm going to hydraulically fracture. So this much sand would be required to be pumped. So this is how you design your uh, what are the treatment key parameters for treatment design? If you are going to design a treatment, what should you be keeping in your mind, right? So in the left column there is information. What information is required, and in right column the source is there. That what are the sources of that information? From where can you get that information? So first, this thickness of the formation that you're going to frac, it is required. So you can get them from wireline logs or your core analysis. What is the permeability of the zone of interest? That is to be known so that you can design it better. So this permeability can be identified with the well test, uh, this production testing or core test. Not production testing, sorry, drawdown tests or core tests. What other information? Temperature, because it can hamper your frac fluid, so you have to know it. So open hole wireline logs, they can tell you about temperature. What is the temperature at the bottom? What are the mechanical properties of the formation? What is the mechanical properties? Means Young's modulus. You must have studied strength of materials. What is the toughness? What is the hardness? What is Young's modulus? What is Poisson's ratio? You have to know all these properties about your formation so that you can frac it efficiently. Fluid leak of characteristics will be of the formation will be basically governed by your permeability, the kind of matrix it has. If it has natural fractures already in the formation, it will have a different kind of fluid leak of profile. So you have to analyze all that. What is the fracture gradient in the nearby zones? You have to uh, know that through a mini frac test. So mini frac test is another different topic because there are different tests which are to be done. So they, if you want, they can be taken in a separate session because it would be a very long discussion. So what is fracture gradient? What is the fracture length that you are aiming for? How much length do you want your fracture to have? So, and fracture height, what should be that? So height, length, and the gradient. So this is basically comprised of your fracture geometry, which can be designed on your designing software. So there are different softwares available in the market. There are different companies which use different kinds of softwares, MFrac, then FracAid, then there is Templan. There are different softwares. So you can use these kind of softwares to model your fracture and just simulate how it will be behaving when you're actually pumping the frac job. So what next is perforation information. So what kind of perforations have been done? Have they been done with wireline? Have they been done with coil tubing? Because the perforations will have different geometry. Some will be the hole size will be big and some will be deep penetrating. So all these parameters will affect your perforation friction pressure. So you have to be aware of that. Wellbore configuration. What kind of wellbore is it? What kind of casing is used, right? And so the entire completion design is to be referred so what are your maximum allowable surface pressures. So this information is to be considered. Fracturing fluid, which kind of fluid you are using, what should be the additives, and in what concentration. Basically, the entire recipe of the fracturing fluid, it should be considered. Fracturing proppants, which kind of proppants you are going to pump. Are you going to pump natural proppant, or are you going to pump synthetic proppant, or ceramics proppants, or and mesh size, the acid solubility, and different parameters that you can vary according to your requirement. And what should be the pumping schedule? I mean, at what concentration should you be pumping the proppant? So what are the phases of frac process? Okay, starting from, this is graph of pressure and time. This can be bottom hole pressure as well as surface pressure. Okay, the profile will remain same. So here at this point, you are starting to pump, you are increasing. So this is time. So as you are progressing in the job, these things will happen. So the pressure first will increase because you're pumping. And at a certain pressure, you will achieve a formation breakdown because the formation will break and it will allow and it will start accepting the fracturing fluid in it. Okay, so at that point, the pressure will start decreasing because you will be creating more volume into the reservoir. Okay, so at the same pressure, if you create more volume, the pressure is bound to decrease. Okay, so first you will be pumping your pad fluid as in the animation I showed you. Okay, so the pad fluid you will pump to here, and then you will start your sand stages. Okay, then you will start mixing the sand in your frac fluid, and then you will continue pumping further. So in this stage, you will be pumping your sand stages up to according to your design. What is the total sand you want to pump? You will pump. and then you will shut down your pumps. So as soon as you shut down your pumps, the pressure drops up to this point. Okay, so this drop has happened because you have shut down your pumps. Now the fluid is not moving at all, and all the friction effects have been nullified. So this drop, it gives you an idea about how much friction you were having while you were pumping the job. Okay, so this is called a step down test. So I'll again explain it in the next slide. So this is an indicator of the friction that you are having in the pipe as well as in the perforations. Okay, so then at this point, what will happen? Your the pumps are stopped now. Now the frac, and this is it. It also gives your fracture propagation pressure. So this is the minimum pressure that was actually driving your fracture, or this is the pressure which was propagating your fracture. So when you start, when you let the fluid leak off further in the formation, it will drop down further and it will indicate a slope change. So this point you can mark as a closure pressure. So at this point you can say that your fracture is closed. Okay, so you stop pumping here, and here from here to this point you just monitored. So the frac fluid just kept leaking off into the formation, and the fracture started closing at this point. And it up to here it has completely closed. So this is the fracture closure pressure. So this is the minimum pressure which is required to keep the fracture open. So if you're at any time in your job, during your job, if the pressure drops below this point, your fracture will close. So you should always be aiming to keep your pressures above this closure pressure. So once you know it, you can design your jobs better. So now the difference between the ISIP, this point, and this point, this will be called the net fracture pressure. So this is the base. This is basically the actual pressure which was driving your fractures further into the formation, because this was just friction. Okay, so this is the actual pressure which was causing the fractures to be created in the reservoir. So this is very important parameter, net pressure. So this is the difference between ISIP and closure. So this is what you should always try to achieve, so that you can so your fractures can grow more in the formation, and you can cover more reservoir while fracturing. And then it is just a normal decline of pressure until it matches with the actual natural reservoir pressure or hydrostatic pressure. Okay. So I mentioned mini frac. It is also called data frac. It is required. See these parameters here: mechanical properties, fluid leak off, gradient, and length. So the source of all these parameters is mini fracture test. So this mini fracture is also called data frac. Some call it data frac. Some call it mini frac. Okay, so this is just a small fracturing treatment just for the data acquisition purpose. It is done without proppant, and just the frac fluid is pumped in the reservoir to assess the few parameters, which are breakdown pressure, at what pressure formation is breaking down, fracture extension pressure, and at what pressure are we able to extend the created fracture further into the reservoir. Fluid loss coefficient, at what rate is the fluid getting lost into the matrix. Okay, so you have to pump rate faster than that, so that your fracture can always have fluid inside it. Then only you will be able to place sand. Okay, otherwise, if your fracture is dehydrated, you will not be able to. If there is no fluid, you cannot apply pressure to it, right? Because it is your medium for the application of pressure. So fluid loss coefficient is to be determined. What is the efficiency of frac fluid? Okay, so how much are you pumping and how much is getting lost? So that will give you, the difference of it will give you efficiency. And fracture closure time, in what time your fracture is getting closed. So there are different tests, okay, which you can do during data frac. This is called a step-up test. Okay, step-up test, it allows you, because you keep pumping at various rates and you get the graph of pressure versus rate. And at some point, the graph will change the slope. Okay, so you can just, by using curve fitting, you can fit a curve to both the trends, and then you at the point of intersection you can get a fracture extension pressure. So you can, when it changes slope, you can say, okay, now my fracture has started extending into the formation. Okay, so this is called a step up test. So there is something called step down test. It is also the result of it is a graph of pressure and rate. So if the graph is concave upwards or convex, so it is called tortuosity dominated. So this is the analysis of friction, the kind of friction that the formation is having. Okay, and if it is the concave graph, then it will be perforation dominated. So it will be called that because of perforation size or dimensions of the perforation, this friction is causing. The other one is called tortuosity dominated. So this is the result of a step down test. So this is how we analyze. So there is, after the frac job, there is something called pressure matching. We, in the software, we collect the data during the frac job, and we try to feed everything into a simulator. Okay, and this is the sort of output it gives. Then you match the pressures. Okay, the pressure trend that you have gone. So this is, the blue line is the surface pressure which you got. Okay, during the frac job, and okay, sorry, this red line is the measured surface pressure. Red line is the actual pressure that you recorded during the frac job. And the blue line is surface pressure, which is, it's a curve that has been fitted with this, this actual curve. So all the parameters are analyzed while you feed this data into software. This particular output has been given by a software called Frac, and it is generally used by baker use. And by doing this pressure matching or curve fitting exercise, okay, you get an idea about the net pressure. I mean, actually what pressure was driving your fracture into the formation. And you also get the formation rock mechanical properties, such as Young's modulus and Poisson's ratio, and you can verify these properties which you have got during this fracturing job through with the data that you have got with your logs. So if they match Young's modulus and all the other parameters, if they match, then you can say, okay, this is a correct match, and this is the correct simulation of a frac job for that particular formation. Okay, so this pressure matching is done after each and every job. So this is the kind of output that these softwares produce. They basically give you the stress profiles and the kind of width that you have created in the formation. Okay. So this is basically a 2D, 3D model, sorry, because there is width and there is height and length. Okay, and different colors, they show different widths here. At what point in the fracture, what kind of width you have created. Right? So this is a 3D modeling of that. So all these things basically are the job of a frac engineer. So he does that, and you cross verify each and every parameter that you have been assuming or putting it to use for the simulation purpose. Okay, and then you correct it if you do not get the desired results. Right. So that was the end of it, guys. I believe you gained something. So that's all from me. So if there are any questions related to this, let's get them addressed.
Yeah. Thank you for the wonderful session, sir. Now we would move on to much anticipated moment from the audience. That is Q&A session. Please drop your questions in the chat box. Only those questions would be accepted which are on the topic, hydraulic fracturing, basics and operational overview.
Okay. Okay, Rahul Pawar is asking what are the flowback additives and how they work. Flowback additives are basically, see, the chemical composition of such chemicals is not revealed by the companies, but how they change the wettability of the formation, and basically they increase the surface tension between the formation rock matrix and the fluid, so that it can be recovered easily. So if there is a lot of the surface tension, if the between the frac fluid and the rock matrix is minimized, the frac fluid will tend to adhere more to the matrix, rock matrix, right? So it would be very difficult to recover such kind of fluid, which is a tendency to stick to formation. So the flowback additives, they basically invert the wettability or the rock wetting properties of that fluid. And these flowback additives are designed keeping in mind the kind of formation that you're fracking and then the kind of frac fluid you're using for fracking.
Thank you, sir.
So next, Trishank, why
Yes,
some?
sir. Sir, I will read on to you.
Yeah.
Why some people are against hydraulic fracturing in USA? Is it having any environmental issues?
So, okay, this is the elephant in the room. So, hydraulic fracturing has, so there are different documentaries available on it. You might have watched Frac Nation or Gasland, or all these documentaries are very popular among the environmentalists and NGO and fracking enthusiasts. So some people are against it because they have some proof that the fracturing has caused the hydrocarbons or the chemical laden fluid to migrate into the water table, groundwater table, and that's why it is polluting the water and it is causing a hazard, which is related to potable water, and it is called leading to the scarcity of drinking water because it is polluted now, right? So, but things are they are claims. So the world is basically divided on this opinion. So at one side there are fracturing specialists, there are scientists, and there are oil and gas companies, and at one side there are environmentalists and there are NGOs and enthusiasts, right? So, and I would share a personal opinion on this because as far as I have worked in oil and gas and whatever employers I have worked with, and so I have not seen any sort of contamination happening in the groundwater because wherever I've worked in West Bengal, I've worked in Rajasthan, I worked in Mumbai, and a bit in MP also. So this kind of problems have not been visible, but you have to be careful while designing your job, frac jobs, so that the fracturing, your fracture design should be able to remain contained, right? It should not exceed your parameters. If it is migrating, your fracture is you have created in some certain zone, and it is migrating into a different zone, then there are chances that it might create such kind of problems, right? But until and unless you have concrete proof, you should not be paying heed to these claims. But it is your, as an engineer, if you are designing these jobs and if you're executing these jobs, it is your responsibility that you analyze your frac barriers properly, you analyze the recipe, and if you can replace any chemicals if they are having hazardous properties, and if you can make use with a different sort of chemical, then you can go for it. I mean, it should be led by technical facts as well as slightly due to moral compass, right?
Thank you, sir. Is it true that hydraulic fracturing is bad and its impact to water reservoirs is big?
So this is basically the same questions.
Yeah.
Actually, the government in all the countries, they also issue the guidelines for the wells which are being drilled in the territory. That's why if you are a petroleum engineering student or drilling engineering student, you will be knowing that we lower the conductor casing and surface casing first, right? And we cement it. So what is the purpose of these casings and intermediate casing? These are basically to isolate your groundwater table. and the depth of such casing is considered after knowing the depth of the water-bearing zones. Okay, this is the main reason. So for well-designed considerations, they should always be having kind of provision so that you do not contaminate any of the natural reserve.
Thank you, sir. I think this is the same question. Sir, can you please elaborate on the fact that how the hydraulic fracturing is affecting the permeability and porosity of reservoir rocks of the underlying basins?
Underlying basin, do you mean by underlying basins? Okay, so basically it's not affecting the matrix permeability, but you are creating a fracture. Okay, you are creating extra space in your reservoir and you are filling it with sand. So now the permeability of that fracture will be equivalent to the permeability of your proppant pack. Okay, so the matrix permeability, it is not altering, but you are creating a separate path for the frac fluid, for the formation fluids to flow into. But the porosity of the reservoir, it is not going to change because you are not uh, altering the formulation of the hydrocarbons or the formation, right? It is, you are just creating a separate path. So whatever it comes under that path or whatever that fracture intersects, it will separate that and it will create an artificial permeability in that path. But the other matrix which has been not which has not been contacted with the fracture, those properties will remain the same.
Thank you, sir. We have next question. Is there any relation between subsidence and proppant selecting criteria?
Subsidence and proppant selecting criteria are different things. Subsidence, it will mean selection criteria is basically the proppant is selected so that your fracture can hold and it can withstand the closure stress, right? So that will give you your proppant selection criteria. Subsidence is differently is in different story. Subsidence will mean that because of fractures, the overlying rocks which are above your zone of interest, they are subsiding or they are sinking further in the ground. These kinds of studies have been carried out between the government bodies and the private players also. And as far as I have seen, there is no subsidence being caused by fracturing. Even if it is a massive fracturing campaign, there is no subsidence being caused because there are evidence, because the volume that you create in a particular formation with the fracture, it is quite insignificant as compared to the volume of rocks which is overlying it, right? So even if you create a small volume, the but because of the overburden stress, the above overlying rocks or the bottom rocks, they expand and they will put pressure on the closed fracture. So and that expansion is very negligible because of the volume of the overlying rocks is so and your fracture volume is quite less.
Thank you, sir. We have next question. If any impact of hydraulic fracturing on water reservoirs?
Water reservoirs, I already told, there is no impact identified in India, but and to keep it that way, we have to follow the government regulations. If you are designing a frac job and the way your wells are going to be drilled and the way your completions are to be designed, because the conductor casing, the surface casing have to be properly laid and properly cemented, and you have to ensure that there is no communication between water tank and the zone that you're going to frac, and ensure that there are proper barriers. Barriers is mean when it will mean that the zone that you're going to fracture, it should have an overlying impermeable zone like shale. Okay, so whatever fluid you're pumping into the fracture, it should migrate to the reservoir, to the formations above that. If there is an impermeable formation which is acting as a barrier, so there is no chance your uh, frac fluid will leak off and it will pass through shale barrier and pollute your or impact your contaminate your ground. Okay. Also, in India, most of the groundwater table is between 200 meters to 700 meters, and all the fracturing operations that I have seen has been done below 1,000 meters and between 3,000 to 3,000 meters. Right. So there's a lot of difference of depth between these two. So there are very little differences.
Okay, thank you, sir. We have next question. What severe kinds of health issues we can get from chemicals used in hydraulic fracturing?
Hmm. Chemical issues. Okay. So each and every chemical comes with the MSDS, material safety data sheet. So you should, before using these chemicals, if first of all, you should not use it if you have not been trained in the chemical mixing procedures properly. You should use proper personal protective equipment like masks, eye protection, ear protection, everything. So there are chemicals which can cause uh, harm to your skin or uh, your health if inhaled or if they come in the contact with your skin or something. So you have to take proper precaution while handling such chemicals and while mixing such kind of chemicals. Okay, so if they are not coming in contact with you, you're fine, no problem. Okay, so you should be having proper training and you should be aware of what chemical are you using and you should have studied the MSDS, material safety data sheet. So it has all the kinds of hazard that that particular chemical might pose to human skin or human body. So you should always keep that in mind.
Okay, thank you, sir. We have next question. Sir, what are the parameters we have to check? What are the parameters we have to check before we are fixing to do hydraulic fracturing? I mean, sometimes production decrease due to tubing size and some other problems.
So, okay, so the first slide was about why you should do hydraulic fracturing. You should be analyzing the candidates, okay, if your well behaving properly, and then only ensure that is it a proper candidate for carrying out hydraulic fracturing because it's a very expensive operation and it's a huge operation. So you should be finalizing that. You should be sure that the production decrease has happened because of decreasing tubing size, or has it happened naturally, or do you have an evidence of having a skin developed across your perforations? Okay, then only you should be going for hydraulic fracture. There are some cases in which hydraulic fracturing, before hydraulic fracturing also you can use some of the chemicals or some acid jobs, oxidization, which can give you equal results. So in those cases, you will not opt hydraulic fracturing is an optimum operation, optimum solution. Right. So what parameters are to be checked? You have to analyze completely that why your production has gone down. Is it due to your artificial change in artificial lift strategy? Have you changed any parameters regarding your artificial lifts? Has the gas cut increased in the well? Is your wells producing fines? Because all these things they can cause production and may not require hydraulic fracturing.
Okay, thank you, sir. We have next question. Sir, do we use same well head for production and fracking?
No, there are different wellheads because fracking you will generally have expected pressures would be higher than your production pressures. So uh, generally while fracking the minimum peak is 5,000 psi and 10,000 psi. Producing the same wells will be having a pressure below 5,000 psi. Okay, so it depends on the well reservoir pressure. At what pressure is your well producing? Okay, so the production tree and frac tree, the production wellhead and the frac wellhead, they are a bit different.
Okay, thank you, sir. We have next question. Sir, is there any side effects of fracking in reservoir life? Example, if future EOR has been planned, could it hinder the EOR operation and future of the reservoir?
For if you have an EOR plan, the fracturing operation will not hamper it because you're not tampering the permeability of the matrix. You are just if even if you are tampering it, you are increasing it. Okay, so the EOR should not be of concern if scanning for a fracture. Okay, because in EOR also you will be if you are using a microbial oil recovery, or because microbes they do not affect your fractures. Okay, or if you are having a in situ and all sort of things. Okay, so they will also not affect your. It's just silica sand or ceramic sand that you're going to use. So there's not. They cannot be a difference.
Okay, sir. Thank you. This would be the last question. Sir, how do we calculate the optimum size of sand particles?
How do we calculate the optimum size of sand particles? Okay.
Yes, sir.
So first of all, when you are going to frac a virgin formation, then you will first run drawdown tests on it, and you will identify what actually is the permeability of the natural reservoir. And if you take a decision on fracking it because you want early production or you want enhanced production, then you will have your type curves, and because of due to after well testing, then you will generate it, and then you will estimate how much permeability is your fracture going to create. And for that permeability to be created, what size of propant and what kind of propant is to be used. So all these parameters come into play while deciding for what kind of propant size should be pumped. Even in tight oil and tight gas, which are extremely tight formations, generally the 1630 or 2040 sands they do, because if you go higher than that size, then the chances of crush they increase. Okay, so there are methods for calculating. There are different curves. So I mean, I cannot show them to you right now, but maybe we can take it up in the next session. Okay, so just know that the size of sand particles, it will depend on the kind of permeability you're looking for, and the other constraint. I mean, the that size of particles you should also be able to transport in the formation. If you are aiming for a higher size but you cannot pump it, then it's of no use. So all the operational and design considerations have to be looked after.
Okay, thank you, sir. Um, we have completed the Q&A session. So now I would pass it on to Nikhil Agarwal to conclude the session. Thank you.
Thanks to all for your valuable time and cooperation to make the event successful. I, on behalf of the Petroleum Engineers Association, thanking Mr. Yes Bhatt sir for his presence and providing us time for his busy schedule. Thanking him for his informative and valuable presentation. Hope all of you have enjoyed this knowledge sharing session. I am thankful to all for your active participation. I extend my big thanks to all my members for their extensive support, and you will get feedback form to your email ID. So please kindly fill that so we can know the further thing. Thanks.
Okay, so I thank you guys also. Thank Petroleum Engineers Association for having me over, and I hope you gained something out of this session. Right, so if there are any further queries, just please get in touch with the PE Association, and they can get back to me.
Sure, sir. Thank you so much, sir, and thank you so much, participants.
Thank you, guys.
Thank you, sir. Yeah, feedback form will be mailed to your corresponding mail ID.